Okay, so I don't know if it will surprise you to learn this is the conferences. I have my own that's identical, and now I'm confused. I agree with much of what Carlos said, not everything, but I've been asked to sort of play devil's advocate here, which is hard to do, because one has to answer every question that we're going to spend all week debating, and then some. Can't do that in 20 minutes. Okay? So I tried to express this dichotomy a bit in a review in which I've quoted myself twice. Given the many compelling successes of the concordance cosmology, the various interlocking but distinct lines of evidence supporting it, and its basis in the highly successful theory of general relativity, it seems quite unreasonable to doubt the existence of CDM. I think that is something that many in the audience would probably agree with, right? But if one looks at it from the other side, one might say that given the obvious organization in the data, the many predictive successes of MOND, and the inability of lambda CDM in many cases to make comparable predictions, it seems quite unreasonable to believe in the existence of invisible mass from beyond the standard model of particle physics that pervades the universe with nary a signal in the laboratory. Because we do need new physics here, one way or the other. We need a new kind of particle that's outside the standard model of particle physics. So that's one of the very few things I disagreed with Carlos. We're just taking for granted that this stuff exists, and we don't know that that's actually true. This is like ether in the 19th century. Given what was understood about physics then, the ether absolutely had to exist. That's where we're at now. This stuff has to exist, but it's an independent question. Does it? That's why it's so important to do these direct detection experiments. That one. Okay, so in the scientific method, predictions are supposed to keep us honest and hopefully objective. And the best kind, of course, is the a priori prediction, something you say ahead of time that comes true. That's the gold standard. There are lots of examples of things that must be so. Einstein's postdiction of the precession of the perihelion of Mercury is an excellent example of that, right? He didn't have the opportunity to say ahead of time, but he showed it had to be that way. Then you can fit things, and that's fine. That's part of normal science. And then there's times when we're just making stuff up. And that often comes up when we have a model that has a whole lot of freedom, a lot of free parameters, right? And of course, epicycles are the classic example of that. And so the title of the conference provoked me to go back and read a bit of the philosophy of science. And the recognition and acknowledgement of anomalies results in crises that are a necessary precondition for the emergence of novel theories and for paradigm change. That's one of Kuhn's things, this whole idea of paradigms change. But the question I've been struggling with for a long time is what counts as an anomaly in cold dark matter, okay? And the things that Carlos addressed, I don't consider anomalies. I consider those puzzles to be solved in the normal, what Kuhn would call normal science. And so I want to give due credit because a priori predictions are the gold standard, and there have been things that I've been impressed with lambda CDM. This paradigm emerged gradually. Certainly by the mid-90s, it was well established to those of us who were paying attention, so much so that, one of the things that really convinced me to take this seriously was a paper by Ostreicher and Steinhardt, though George Staudieu had already gotten the ball rolling earlier than that, and there are a number of other papers, Yoshi and Peterson, for example, and basically, from all the data that we had at the time, you say, really, that's the only allowed region. That's what we now call lambda CDM. And I was kind of shocked by this and said, geez, if that is true, then we actually would predict that the expansion of the universe is accelerating. How crazy would that be, right? So I actually wrote a paper in '96 saying, geez, we really want to go there? This sounds crazy. Well, of course, that was a prediction that came true in the supernovae. Now, this is what I think pushed it into the wider appreciation that we had to have lambda CDM. But I was still nervous about this because a lot of the things we were doing at the time just sort of assumed that the geometry was flat. And the supernova by themselves data didn't really tell you that. So I was really relieved. We expected the geometry would be flat, and that's exactly what you see in the CMB. That was another prediction that was confirmed, and you can go on from there and get the BAO scale right. Those are all a priori predictions which come true and go a long way to convincing me that this is the right approach for cosmology. Now, this keeps coming up and up. It's not like we don't think about this. That the fluctuations exist at around this level is certainly an a priori prediction. Getting the details right is an important and hard thing. That the location of the first peak is just where it is a very impressive a priori prediction. I tried to work out what would happen at that time if you had something motivated by MOND. Now, MOND's not in this at all. This is just a model without dark matter. Compared to what lambda CDM at the time predicted. And the big range here for the lambda CDM predictions was driven by the uncertainty in Big Bang nucleosynthesis. But for the full range of BBN as it was known at the time, this was what was predicted. For that same range, this is what the no CDM prediction was. And you see there's no variation there because basically the models just pile on top of each other for the range of BBN. Okay, so I predicted that a priori. Nobody else did that. Okay? Just like a little bit of credit, even if it's wrong. Because the other thing I said was that eventually this ansatz that I made, very simple ansatz, that ansatz had to fail. Well, so it fails at some point. So you can rule out that ansatz, but we knew that had to be the case. Okay? So, maybe there's something to it, or maybe it's just a really huge fluke.
Stacy, can you say, this is not a success of CDM, right? So, for example, warm dark matter would give you a flat universe, it would give you the peaks, it wouldn't be any otherwise. Much so like CDM, the flatness existed before CDM was thought.
Well, okay, so you're downgrading my tree. Okay.
No, I'm just saying that the flatness and the peaks doesn't tell you CDM is there.
It tells us the geometry is flat, and that is consistent with the prediction of the paradigm we had developed to that point. It's not the only way you could do it.
Exactly.
Yeah, that's right. So just the facts, just the data that I think are important to explain as it pertains to this particular debate. Rotation curves are flat. You have this baryonic Tully-Fisher relation, Renzo-Sanchisi's rules, the central density relation, the radial acceleration relation. These are all now well-established empirical regularities that you have to explain in any theory, just like you have to explain the CMB in any theory. We want to do everything. Now, though these have in some form or another been known for a long time, only the first one really informed the development of the dark matter paradigm. And I think I agree mostly with what Dan said. It is convinced us that there had to be something dark. You needed the cosmological arguments to convince us it had to be something non-baryonic. That's an extra piece. But if you had known all of these things at the time, you might have thought differently. So you always have to cast yourself back and do that. Okay, rotation curves are flat. I won't belabor that. But you do notice that big galaxies rotate fast, small galaxies rotate slowly, and that leads to the Tully-Fisher relation, which fundamentally is a relation between the baryonic mass, these things, and stellar mass. These things are mostly made of gas, so it looks like a messy relation here. You add in the gas mass, it's one nice continuous relation over many decades. Renzo's rule, Renzo-Sanchisi was a great radio astronomer at Groningen for many years, and he sort of summarized his career in one sentence, that when you see a feature in the light, you see a corresponding feature in the rotation curve and vice versa. And this was the wisdom accumulated after decades of doing this kind of work. Renzo was a really sharp guy, so I took it seriously, and we had big arguments about this. But there are a couple of examples. This bulge component, you only notice in the near infrared, it's only 4% of the light, but it's also compact, so it causes that little tweak in there. That's an example of what he's talking about. But what we argued about was that, we started seeing these kinds of features in low surface brightness galaxies where the discrepancy is large. And most of this mass should be dark matter in some quasi-spherical halo, which does not sustain that kind of feature. And yet we were routinely seeing this match kind of thing. The other thing I noticed, and my postdoc Federico Lelli has quantified very nicely recently, is that the dynamical mass, surface density, at the center of galaxies correlates with the surface brightness. The lower the surface brightness, the lower the dynamical mass, but it's not just one-to-one, except at the bright end. You still need some dark matter in here. But the amount you need knows about the amount of light. Okay, it's not just something that happens. And this is a thing generally true throughout the range of galaxies, that the surface density, so these very low surface density galaxies, very high surface density, that correlates very well with the shape of the rotation curve. It's just that perfect rainbow that you can see with your eyes corresponds to the surface density. Not the mass, the surface density. The mass just corresponds with that Tully-Fisher velocity. But the whole thing depends on the surface density, the distribution of baryons, which is what we quantify here in the radial acceleration relation. I'd be happy to spend 20 minutes just talking about how we obtain that. But the point is that the total acceleration correlates really well with the, what you expect just from the stuff that you see. Now, what I think might be anomalies are basically fine-tuning problems. It's very hard to outright falsify the idea that you have invisible mass driving the dynamics. So sort of the worst thing you can say about it is it faces a fine-tuning problem. And I first became concerned about this with the lack of size residuals in the Tully-Fisher relation. Basically, if you know m and v, that's it. That's right on there. There is no residual from there. There appears to be no intrinsic scatter, or at least very little. Same thing for the radial acceleration relation. The entire distribution of dark matter is fine-tuned to that of the baryons. And then finally, just that, why the heck does this crazy theory get anything right? So let me talk about that in a little more detail, just for you to think about. These are the residuals from the Tully-Fisher relation. This is what I had naively predicted should be the case, and there's a really good fundamental reason for that. The velocity depends on the mass over the radius. We got two components, the baryonic mass and its scale radius, the dark mass and its radius. And in order to keep that constant, if this goes down, that's got to go up, exactly to keep it tuned. Right? So there's a big range, there's a big scatter in size at a given mass, velocity. This galaxy's compact, that one's not. But you can't tell that from Tully-Fisher. So that bugs me, but I invite you to think about that on your own. For the detailed distribution of dark matter over the range of radii that we observe, we've shown that you can just basically write a function that describes the total observed acceleration in terms of what you expect from the baryons. You can rewrite that in terms of the dark matter, and you can get an expression for what the acceleration due to the dark matter component is, expressed entirely in terms of the distribution of baryons. What the heck, man? Right? The baryonic tail is wagging the dark matter dog. And you can't turn this around. You need to know what the distribution of baryons is. And this holds even for a galaxy that entirely lives down here where it's completely dark matter dominated. Seems like an anomaly to me. That's just really weird. All right, so in the 0 time left, I will talk about this crazy theory, which I had the same reaction as most of you. It just can't possibly be true. The idea is that you modify the acceleration, the force law at some low acceleration scale, and of course this was constructed, motivated by flat rotation curves. So it does that. That's not a test. But the Tully-Fisher relation is something that Milgram predicted in 1983 had to have this absolute form. Now, Tully-Fisher was known to exist at the time, but it was not known in any of this kind of detail. The slope did not have to come out right. The normalization didn't have to come out right. These are all gold star predictions with the exception of the normalization, which you have to appeal to the data to fit, get the absolute value of that. But basically, there is no dependence on scale length or surface brightness, the thing that had confused me so mightily in the conventional context, in which I invite you to think about. That's an a priori prediction of Milgram's, and he was the only one who made it ahead of time. There's also no scatter as far as I can tell, and that's because in this paradigm, it is an absolute consequence of the force law. I would expect if these things are getting their velocities from dark matter halos, then there ought to be scatter from halo to halo, even at a given mass. We don't see any evidence for that. Renzo's rule follows very naturally. Basically, MOND is a rule that tells you how to map from the distribution of predicted accelerations to what you get. And that's something we need to understand, even if this is not correct as a theory. And if you think about it, that's really hard to understand unless this is correct as a theory. One prediction that Milgram explicitly made in 1983 was that the shapes of rotation curves would depend on the surface density. They would go up if they were high surface brightness very sharply, fall a little, and flatten off quickly. Whereas if they were low surface density, they'd rise very gradually and only slowly turn around. It's exactly what we see. In 1983, these data didn't exist. The low surface brightness galaxies he was making predictions for were thought not to exist either, because most of us believed in Freeman's law at the time. It said all spiral galaxies had the same surface brightness. The radial acceleration relation I've been trying to put, this is just purely empirical, right? Okay, you don't want to consider MOND, I get that. But what do the data say? And so we could see this already in 1998, just a couple dozen galaxies. I came here after writing this paper in 2004 explicitly to talk about this. This was largely ignored. And so now we have that there. And this is just the steady improvement of data. There are more galaxies, better mass models. But in MOND, you can actually use the distribution of baryons coupled with the force law to predict what the rotation curves are. The only free parameter you have in this exercise is the mass to light ratio. And so even when you have these little wimpy galaxies, they're low acceleration, so you get a big correction. And you can do this an arbitrary number of times. Each galaxy is an independent test. I often hear people say, oh, MOND was designed to fit rotation curves, so of course it does. That's a myth. It's just not correct. Once you write down the force law, you're stuck with it. And you observe the baryon distribution. This is a very restrictive thing. So it's sort of like having the CMB an arbitrary number of times and only one free parameter every time. And so if you do this, all of a sudden the scatter goes away here because you're fitting out the one major thing that contributes to the scatter, which is the mass to light ratio of galaxies, which is very consistent with what you'd expect from independent stellar population information. I would love to tell you that this was wrong, and maybe there's a hint that it is out here, but that, this is exactly what Milgram predicted. I would love to tell you something different, but that would be dishonest. So I've tried to test this in more places. The dwarfs of Andromeda. A very peculiar feature of this theory is that it has this external field effect. It depends on, for a dwarf orbiting a giant host like Andromeda, it depends not only on the internal accelerations of the stars, but the fact that the dwarf is orbiting the host. Both of those accelerations count, and it changes the mass estimator. You have to keep account of that. But so we actually did the exercise of predicting these velocity dispersions in this way. And it worked out remarkably well, including many cases that we were able to publish the prediction in advance of the observation. Okay, that's how we're supposed to do science, right? And this one I've given 2 stars because we actually called out Andromeda 28 as a really good case because it's far enough away from Andromeda to be isolated, so the uncertainty in the prediction is really good, and then boom, there are 2 confirming observations right after that. Now, this external field effect is unique to MOND. It's going to be very hard to mimic this in any kind of dark matter theory. So you can actually match up pairs of galaxies that are photometrically indistinguishable, but either do or do not feel the effects of this external field force, which leads to a difference in the predicted velocity dispersions, which you can start to see in the data. It's not like this is a 5 sigma effect. but you can start to see that, and it's really, really unique. Same thing for crater 2. I do both sides. I worked really hard to try to predict what the velocity dispersion would be here in lambda CDM. It's hard to do because there should be a lot of scatter in the halo mass at a given luminosity at these low luminosities. But it should have been high for this thing. MOND predicts this ridiculously low velocity dispersion, just a couple kilometers a second, and that's what's observed. And I can tell you that in advance. And I did that for a bunch of the other Andromeda dwarfs. There was this case of a dwarf recently reported in Nature. An upper limit of the velocity dispersion was placed, had to be below here and more like 3, something like that. The MOND prediction is over here, 20 kilometers a second. Clearly wrong, yeah? Except they did both the calculation of the velocity dispersion wrong, and they didn't do a very good job of estimating the errors. So independent people have done, one, tried to reanalyze the data, and that's sort of what this realization gives. And we did the MOND prediction correctly. And now, instead of being wildly discrepant, you could have claimed this is a brilliant success of the theory. Okay. And I cannot tell you how many times I've come across this in the literature, where I read the paper, it looks, wow, this is absolutely wrong. No way MOND survives this. And then I do the calculation myself. It's like, dope. Same thing for the ultrafaints. Here's basically, these things should lie on the line. And I thought, this was a paper from 2010, I thought, okay, I've got it now. MOND clearly can't explain that. And I almost wrote that when I thought, well, wait, now didn't Brada and Milgram do some simulations? And sure enough, not only did they do simulations of dwarfs orbiting hosts, but they give a criteria for when the things become unstable, they're tidally affected and get disrupted, and all the ultrafaints are in this regime where there are basically so few orbits internally to everyone externally, they don't have time to virialize, and they just fall apart on orders of gigayears. And so I was like, well, geez, then what do these things look like? Well, they're all messed up. So basically, MOND tells you when it's going to fail, and that those things are going to fail because they're getting tidally beat up, which is, of course, the same thing that has to happen in lambda CDM, but in MOND, I have a quantitative criterion to know when to expect it. So I thought this was going to kill it. In fact, it looks pretty good. So, I can't talk about all these other things, but MOND does a lot more than just galaxy dynamics. Not time to go in all that. I was just reading Sanders' 1998 attempt to do some cosmology predictions, and it's prescient. He said the first galaxies would be in place by Z of 10, so reionization would happen before that. The contemporaneous prediction of lambda CDM was that no structure would form before redshift 7. So my philosophical puzzle is, why does this happen? And it just doesn't seem to me that it's something that can easily be ignored. And it turns out that Lakatos was a philosopher of science who actually put this in a way that sort of expresses my feelings pretty well, that a research program is progressing as long as it's making predictions. But it's stagnating if it only gives post hoc explanations of facts anticipated by a rival program. For galaxy dynamics, that's what lambda CDM is. We did not predict the radial acceleration prediction in lambda CDM. We can explain it, but we're just sort of reinventing what Milgram already told us. So that's unhealthy. So just to leave you with another prediction, because I do believe in making predictions, this is the predicted signal for sky average 21 centimeter absorption in front of the microwave background. During the dark ages, you get an absorption signal because just a collisional redistribution of the 21 centimeter line occupation levels. So that's expanded here. When the first sources appear, then you get that effect again. And long story short, I expect about twice as much absorption along the line of sight in the absence of dark matter. Okay, so you hear it here first. We'll go out and test it, and hopefully one of those will be right, the other will be wrong. So we can start debating. I don't know if this is plugged into the audio, but this is really hilarious, so I'll take a minute. I don't know how many of you know Tom Shutt, but he works on dark matter detection experiments. This is his daughter, Maddie, about a decade ago. This is my daughter, Isabel. Now, of course, we both would claim that we don't bring our work home. But one day we had been at a conference and the kids were having a birthday party. I met Tom because our children were best buds. And I walked into the birthday party and from this conference where I'd just been talking to Tom, and I saw Maddie, and I said, "Oh, hi, Maddie. I was just working with your father." And she looked at me and said, "I thought you worked against each other." And Isabel wasn't going to let that stand, so she leapt in, and the following debate ensued. This, of course, is staged because Tom got obsessed with reproducing it after I told him, but I don't know. We'll see if we can hear anything.
If I were getting into the idea that dark matter doesn't exist?
Dark matter does too exist. If dark matter didn't exist, then the eighth dimension would not fit into the quantum theory. No. The eighth dimension does not be divided by 4. The quantum theory of
And that sort of summarizes the last 2 decades of my career. So thank you for your attention.
So there were also other claims in the literature that MOND predicted a much longer time delay between the observed electromagnetic signal and gravitational wave signal from the neutron star mergers.
Yes.
So I was wondering what, the much larger one than was observed. So I was wondering what's your opinion about that?
So I think what the data exclude are models that have gravitational wave times travels much different than the speed of light. That's not specific to MOND. I'm not aware of any sensible attempt to write a relativistic theory of MOND that actually does that. I'm aware of unsensible attempts that just try to do something. But so this is a problem that happens a lot. MOND in itself is not a relativistic theory. It doesn't even predict that. But so what that tells you is you can't write a relativistic theory that does that, and that really restricts the parameter space. I would love to say that makes it impossible, but I don't know that.
So you had a brief red mark with clusters of galaxies. Is that the critical acceleration or the relaxation time, or is there something new?
No, it's the mass discrepancy. So, people like to point to the bullet cluster for this, but this picture is already in our review in 2002, so these are clusters of galaxies, and that's the Newtonian value, and conventionally you infer dark matter. In MOND, this doesn't center on the line, right? So this is the same problem, and so the bullet cluster just shows the same problem that every other cluster also shows. So I think that's a real problem for MOND. But it's, you got to keep some context here. So I think Tony pointed out, well, geez, there's this factor of 2 difference. Yes, that is real. And maybe that kills MOND. And we can see the dark matter in the bullet cluster, but we cannot see that it's non-baryonic. There's nothing about that guarantees that the unseen mass is non-baryonic. And we know that we haven't found all the baryons, and if you sum up how many you need to fix this problem for MOND, it easily falls within the bounds of how much we haven't found. Do I like that? No, of course not.
But there's also the separate issue that the relaxation time is the crossing time.
That's a good point. I don't know. I can't answer that offhand. I would just point on this, because people throw it in my face all the time, that, lambda CDM does great here. Well, baryon's missing there. So we are stuck with a missing baryon problem in both theories.
I'm trying to keep my voice lower than Maddie Shutt.
Yeah, I couldn't control the volume on that. Sorry.
She's very quiet now, I can tell. But I wanted to ask, and I've forgotten, for those of us that do experiments on Earth rather than observations, what can we do to test MOND in an Earthbound experiment?
I wish there were something that I knew, and this is one of the frustrations of it, because the slide I went very, very far, the regimes of MOND, if the external field is very far above A naught, then any subsystem that you build, even if it has sub A naught things, is still going to feel that, and it's going to behave in a normal fashion. So ideally, you'd take that and send it out into the depths of intergalactic space, so have your long-term programs done. I have a chap named Iorio worked out that there was a time when all the vectors canceled such that you should get a Mondian patch sweeping across the surface of the Earth at a certain latitude, like Greenland, at a certain time. And so in principle, you might be able to put the right experiment there and see a glitch as it go by. I have not tried to reproduce that calculation, so I don't know how serious that is.
So the problem is just creating a laboratory where the other acceleration is banned.
Exactly. Yeah. So in Tevis, which I think is already ruled out, but in Tevis, the effect happens where the potential gradient goes away, so you could go to a Lagrange point between a planet and the sun. So there are ways you could do it, but it's...
Some random asteroid may screw it up.
Yeah, it's in that way, it's like the dark matter experiments. You got to shield it from everything else in the universe, and it's really hard.
Okay. So
okay.
let's thank Stacy. And then we can open up a general discussion on the subject of both talks. So, yeah.
Oh, I don't want to stand. I've been standing here.
I guess the local galactic acceleration is right about at A naught, right?
Yes,
so
that's
so I mean, so you can still see some anomaly. It's just suppressed.
Yeah, we're right in the transition region.
Will Pioneer get into an anomalous regime?
I don't think so. Some people hyped the Pioneer anomaly as a MOND effect. I never bought into that because it's huge compared to what MOND predicts. You need to get about 1/10 of a light year away before you might hope to see that.
So there are some unexplained things about galaxies, like for example this M sigma relation, where it's sort of confusing how supermassive black hole knows about the whole mass of the whole halo, and some people say maybe it's because baryons are somehow communicating the information through outflows or whatever. So I mean, is this phenomena that baryons know about the total matter distribution really surprising? And I know Eagles has an explanation for MDAR. What is that? What can you remind us the explanation, and what are your thoughts on it? Yeah.
So I'm open to that sort of thing, but you have to demonstrate it, and it's hard because it's the same thing that Carlos pointed out. What they predict really well is the dark matter side. What we observe are the baryons, and you got to know how to bridge that gap. And what I can tell you is there is that relation. And I challenge you all to think about it yourselves, what that means. Because it's very easy to say, oh, well, the dark matter tells the light how to move. But that doesn't actually provide an explanation. It sounds wise, but it doesn't work out. So, maybe something like, the simulations will do this, but I would like to understand physically why that happened. So maybe I should let Carlos.
I think she was asking about AGN feedback, right? So, but let me come back to Stacy's point. But in another context, when I talk to galaxy formation theorists, I often make not a huge deal, but a little deal about the fact that the AGN feedback was in a way not quite a prediction, but very early when we were trying to understand, not just me, but other people, the community, why the galaxy luminosity function bends over as it does. In those days, there was a mystery with cooling flows in galaxy clusters. And there was another mystery, which is that in standard, just naive CDM theory, the galaxies, the biggest galaxies you would expect to be blue because they form late, so they should still be forming today. They should have young stars. And we observed exactly the opposite. The big galaxies are red. So there was this dichotomy, this sort of puzzle of why are the biggest galaxies red, not blue? Why are there no cooling flows in galaxy clusters? And why does the luminosity function turn over? And it turns out that various ideas were floated, and AGN feedback was one of those. And in a way, it kind of came way before all these subject developed, and now we do know, and we observe. In fact, it was before Chandra when Chandra actually saw the bubbles produced by the feedback coming from the black hole. So I would say this is a minor success of the theory. But let me just make a contact with the way Stacy answered the question. So reason, I think Stacy is correct when he says that often in CDM theories, look at an observation, so what can I explain this within the theory? Now, the key point here is the following, that most of the things we observe involve stars. Stars involve baryons. Baryons are complex. And it was only recently, with this breakthrough that I mentioned, that we have the ability to make detailed predictions for, say, the dynamics of galaxies and so on. And so, until recently, well, we know what the dark matter is doing, but that's not what we observe. And so, it's only now that we're beginning to understand the kinematics of galaxies and so on from the simulation program. And many of the points that Stacy makes, for example, about the MDAT relation, so where it matches, where you see at the high acceleration end that the gravity, total gravity, agrees perfectly with the gravity due to the baryons, but would agree with that because we know that in the central parts of galaxies they are dominated by baryons. So it's not surprising that we see the acceleration in the central parts where baryons dominate over the dark matter to be responsible for the total acceleration. Some of the features you see in rotation curves are also a manifestation of the same phenomenon. Now, what I disagree with Stacy, he kind of puts the theory down saying, well, you react, instead of making predictions, you make postdictions. Well, I think, I'm sure Stacy would agree that that is part of science. So you make new observations, you see, well, I have a theory, can I account for these observations? So I think to me that is a perfectly reasonable way to proceed as scientists. And but some of these predictions involving baryons, as we saw, are complicated. And so that's just the way things are. So MOND in a way is much simpler because it has no dark matter. And you see the baryons and you make inferences from what you see. Whereas for CDM theories, because it's the dark matter that dominates on large scales, and you need to understand now the interplay between the dark matter and the baryons, and that's complicated. So that's I think, why sometimes we have to try to explain the data after we've seen the data. But there are many predictions that have, as Stacy himself recognized, being made before there was any data.
So a quick question for Stacy. You showed a nice plot of this A0 parameter across a very wide range of scales, and far on the left of the plot you had the dwarfs, which I assume you mean gas-free dwarfs.
Yeah.
And these have a very large scatter.
Yes.
These have a very large scatter in A0. And I can appreciate that on cluster scales you could say, there may be baryons I can't see. But for those nearby dwarfs, we've looked. There is exactly what you see. So does that scatter in A0 worry you?
Well, on that end, not really, because that's a fairly old plot. I would like to update every single plot I show every time. I just can't do that. So there are a lot more dwarfs now, many of which are the M31 dwarfs that I showed you. And so in the classical regime above about 100,000 total luminosities, I think it's fine. I think the scatter gets bigger because the data get grungier, and not just the data per se, but the accuracy to which we can trace the potential in the way we're doing. Below that scale, which I didn't have at the time, then you get the ultrafaints and they all kick up in the way I briefly discussed. So, if those systems are in equilibrium, then yeah, that worries me in the same way. But I think the dwarfs are mostly a success story. I think there's an important point that Carlos will raise, so I'd like to ask him and Julio and Kyle. So there's Kyle's paper from a few years ago that pointed out diversity in some specific galaxies that didn't follow the Eagle predictions. But then from Eagle, you do get the radial acceleration relation. So I'm wondering which paper I should believe. But I can't because as I pointed out, I think I wrote Kyle and Julio to say this, that some of the galaxies that they pointed out as disagreeing with the Eagle simulations define the RAR. And so you can't have it both ways, Carlos. So which is it?
Well, look, Julio wants to answer, but
Yeah, please.
Comment, Josh, on this?
well,
Yeah, I think there are galaxies that clearly are in disagreement with some of the simulations. Whether the origin of the discrepancy is still unclear to me. In some cases, I think we can point to the fact that the circular velocities that have been derived from the measurements are, I think, patently incorrect. In some cases, actually, it's very obvious that that is the case. In other cases, we are not sure, and the analysis needs to be done to a level of sophistication that we haven't done yet. I think we have some ideas as to why that might be the case. In other cases, maybe the simulation actually failed. For example, we know that some simulations, assuming different parameters than the ones we do, lead to different rotation curves than the ones we predict from the Eagle-like or Illustris-like models. So I think it's still something to be understood there for sure. But I think it'd be premature to argue that this is not, this is not the death toll for lambda CDM. On the point of the MDAR, I think you actually take the points in detail, and not just from the ones that you've done from Spark, just take the actual data from, say, little things. You'll see that many of the galaxies that are discrepant with lambda CDM are also heavily discrepant with the MDAR. Basically, most of the cores, the very pronounced cores in IC 2574 and GC 3917, the examples that I used in my own paper on this, show that the inner regions of the galaxies are way off from the MDAR, way off, by, many, many sigma. Whether you believe the sigma or not, that's a different question, and I think we're going to get to that. So if you just take the data face value, that is way off. And the reason why it doesn't appear in your plots is just because you have linear sampling of the rotation curve that heavily disfavors the inner regions, so they're only representative of one or two points that are way off from the line, and therefore don't get weighted in the average. So that's kind of a long answer for that. So.
Well, so that's a really important point, because the thing's mass models are not the same as ours. So if we go through and put what we would have said the mass to light ratio is into the thing's data, then you get back the MDAR that we got.
Okay, can I just make an observation? Because I think probably most people are lost about this debate, which is very provincial. But so what Stacy, so the two papers Stacy referred to are the following. There's one paper, Kyle is the lead author of that paper, where we showed a plot of the mass contained within 2 kiloparsecs of a sample of galaxies against the measure of the total mass, Vmax, right? What that plot showed, we then had so we had some predictions from Eagle, and we had a collection of data. And what we showed there is that about 2/3 of this eclectic collection of data follow exactly where Eagle galaxies should follow, and then it's about 1/3 that's scattered off. And so then Kyle wrote a second paper analyzing in detail some of these ones that fall off the relation you expected. And he concluded that the data could easily be misinterpreted because you're trying to infer some very delicate, very, very subtle quantity, how much mass there is in the central parts, from observations of rotation curves. Galaxies are asymmetric. They have non-equilibrium velocities. And when you model all that, as he did, he became an observer for a while and analyzed the Eagle galaxies as though he was an observer. And he found that even though these galaxies would have fallen if you knew everything in the predicted relation by Eagle, when you treated them as observers, they would scatter off. So that's one paper that Stacy said, should I believe that? I think you should, and I encourage you to read Kyle's second paper. Now for the MDAR, as Julio just pointed out, the discrepancies that Kyle identified in the very central parts of galaxies, whereas in the MDAR relation, they're only a small subset of the points. So I think you should believe the two papers. They are just the predictions that the theory makes, but they're in different regimes. But what I think is interesting is the point that Kyle has raised, which may be a lot of the H1 data, where people use that to infer the structure of the dark matter halo, may be misinterpreted because galaxies are more complex than we think, due primarily to deviations from simple assumptions of equilibrium and spherical symmetry.
So now we're really debating and telling each other to read each other's paper, because if you read Federico's long paper on this, we model the distribution of errors and the velocities both as a random component and a systematic due to non-circular motions, and that actually explains everything consistently. So the detail, there are two details that are important here. So on the point of diversity, it's kind of funny. When Kyle wrote his first paper on diversity, I had angry people emailing me saying, you should write a rebuttal. I'm like, I gave him a lot of the data, and I agree with what he says. Why would I write a rebuttal?
Sorry.
Oh, sorry.
I thought you were finished.
Well, no. I mean, I should probably let you talk, because I'll never be finished. But I think this is an important point, because if you measure velocity at a fixed radius in kiloparsecs, then you will infer diversity as Kyle has described it. If you take account of the light distribution, that is, you measure something like radius in scale lengths as measured out by the light, then those rotation curves will fall on top of each other, even the ones that you inferred to be diverse in terms of KPC. And that's what's encoded in that central density relation that I told you. The low surface brightness galaxies start out rising slowly, the high ones start out rising. And so you see that difference at fixed kiloparsecs. But it's uniform, not diverse, if you normalize by the light scale length. So the other point about, I'm still concerned about the Eagle explanation for the radial acceleration relation, because the G dagger that you guys fit is 70 sigma off of the observed value.
We understand that, as you know, Stacy, because there's a second paper. That's the paper. So we've done two papers against my better judgment on MDAPs. I knew Stacy would say what he just said. So the first paper by Ludlow et al. Showed that the MDAP relation, post-diction, I'm not claiming this great success of CDM, agrees quite well with the data, but not perfectly. There's an offset. Now, the reason, we understand the reason for the offset, and in a subsequent paper by Julio et al., then we explain why it is. And the reason is that even though the Eagle simulations almost match the stellar mass function, they don't match it perfectly. And it's this mismatch that at a given halo mass, the stellar masses are not quite right, that explains why this normalization is slightly off. So if you correct for that, then they fall nicely on the relation. So I think that's the explanation for that.
Well, that may well be true, but I guess this is an example of what worries me about the paradigm, is that there's always another tweak.
Well, look, it's not a tweak. I mean, this is just, this is what happens. But the point is, would you rather, when you observe something, that all CDM theories just ignored it? Of course, we ask ourselves,
I'm kind of used to that, Carlos.
Can the simulations agree with it? As you know, we've so many times been inspired by your data. So you know, I think the development of the subject is such that we begin it. So many of the things that you point out in the data are very delicate, very precise and specific phenomena that you measure. I think it's perfectly normal in the course of developing a theory that when new data comes, you say, well, does this make sense? Do I learn something? Yeah. So for instance, trying to match the MDAP relation, we learn a number of things. We learn, for example, that the fact that the mass function doesn't quite fit translates into an offset in this G dagger quantity. We learn, for example, that tidal effects are important. So the dwarf galaxies, you talked about these external fields. Now, Julio maybe wants to add something to this, but the way you understand things like crater 2 and so on in CDM, which we wouldn't have predicted beforehand, we could have done, but we weren't thinking of crater 2, has to do with tidal disruption of satellites as they fall in. And these are complex dynamical phenomena. So, but you know, I don't feel embarrassed that you produce some data and then we go and try to see whether it makes sense or not. I think that is the way we will uncover problems.
Sure, that's fine.
I don't think we will uncover anything fundamental about CDM, but we're learning a lot about galaxy formation, about gas dynamics, about stellar dynamics. And I think that is one of the rich parts of the subject. We have now a theory that you can use to try to improve. But I don't think we're questioning, at least not in the stuff that we do, the paradigm, but the simulations we have. And based on the paradigm, we're trying to understand more of the subtleties of galaxy formation.
Well, so, and I agree with you. One of the things I've been impressed with by the simulations that have addressed that is how small the scatter is. I thought that would be very hard to describe. I think that's still an important check that I invite you all to think about. But, you know, it's doing better than I expected. I'll give you that. How's that?
So you asked for new data. Actually, I have to say, in context, I find baryons annoying. Excluding this room, yes. So the new data is a prediction of the CDM model, but on a very different scale than what we've been discussing, but in an environment where there are, as far as I know, very few baryons. And that is the nice filaments that are seen in the CDM simulations have been imaged with gravitational lensing. And they look pretty much the same, given our poorer resolution than the simulations, to what is shown in the CDM calculations. This is a very low acceleration environment. So it would be fun to try to address those data with a MOND-like model, even in the absence of a relativistic theory.
Milgram has done a lot of that work. I don't think he's done that specific problem, but there are papers about it.
So this is going back to this comment about looking at galaxies that don't actually match up with your expectations. So Carlos said 1/3 sort of scatter down, and then you look at one of the individually one by one, and you can make up reasons for why they don't agree. First, I think that's a dangerous game to play, because you sort of know where you want to be, and you're looking at objects that don't agree with you. The second thing that I don't find it compelling is because the places where you actually see galaxies having large cores, like Stacy pointed out, are the systems where the surface brightness is the lowest. So until you tell me why you're screwing up the galaxies in a systematic way, I think this is a non-starter. This is basically like, I know what I want to get, and everything else that doesn't agree with me, I'm going to try and tweak things, right? So I think there has to be a systematic reason for why it's the low surface brightness galaxies that actually have the largest cores in them.
So we corresponded about this. When Carl's paper came out, I got an uncharacteristically direct email from his man. Now look, I think there's a lot of truth in what you say, but I think the essence of your argument is incorrect. And let me tell you what we did. I don't know if you've seen Carl's recent paper. It's on the archive, right? Or were you shy to put it on the archive? So what we did there was something quite simple. We are trying to understand the anomalies that Stacy highlights. Anything wrong with that? No? So you haven't, but many people have written hundreds of papers about the anomalies in the CMB. I think that is something you have to do. So when we found these galaxies that looked not quite as we expected, we tried to understand them better. Okay? Now, we set up the methodology from the beginning. We've teamed up with an observer, Antonino Marasco, an H1 observer, and Carl then turned these galaxies into observational data cubes. He provided, well, he did a lot of analysis himself, but he and Antonino treated these mock data cubes that were made from the simulations as though they were real observations. Okay, so it seems to me methodologically that is a irreproachable approach. We made a mock catalog, and then we used a code called 3D Barolo, which is the code that H1 observers use to infer the potential from the 2D velocity field of the H1, which is what Kyle processed. And we said, well, what would an observer have inferred? Okay? And what we found is that you take some of the galaxies that lie in the relation, and for a subset of those, you would infer that they have cores. When they don't have cores, we know they don't. So, to me, I don't see any flaw in that methodological way of approaching things. I would agree with you that we look at the anomalies. Obviously, that's where we're going to learn something. We might have learned that the theory is wrong, which is what we're trying to do. Believe me, at least my personal approach, I'm trying to disprove the paradigm. I've been trying to do that for 30 years, and that, I think, is the correct way to do science. You look at things that are anomalous. You cannot rule out the theory with this. And as it happens in this case, we couldn't.
I'm not disagreeing that. You want to take anomalies seriously, but what I'm disagreeing with is that you look at a few galaxies and you say, okay, here's maybe a reason why there may be no core in them. I don't think that's enough, right? You need to have a model that actually then sort of goes out and predicts how I would rule this
So here the devil's advocate, no, sorry, the voice of reason is about to answer that question.
Yeah, so that's basically the plan for paper 3. So, I mean, we'll talk here. Unless there's somebody in line ahead of me, though, I have a question. For these guys.
So can we say this is a methodological thing? Just one quick thing. So we made a big effort the day before the DR2 Gaia data release to take our best simulations, turn them into mock catalogs, and put them out there in the public domain in a way that looked just from selection effects and errors and so on, like the Gaia data, right? So here is the theory, here's what the theory predicts, and I would invite you to go and find discrepancies with the Gaia data, because that's how we will advance, and that's where we will learn something.
So I can find common ground and summarize both your talks with the simple phrase, everything fits. And so to try to look to the future and find something that distinguishes, if MOND is right, will the breakthrough microsatellites get to Alpha Centauri?
So these are the ones that are supposed to be seeding bacteria?
Yes.
No, the ones that, yeah.
No, the ones that are supposed to go and observe. So
take a picture.
You're going to fire ballistic satellites to Alpha Centauri.
So Phil Lubin has a great plan to accelerate these ground weight microsatellites.
That's ballistic microsatellites.
Yeah.
So will a ballistic particle going toward Alpha Centauri get there if MOND is right?
I don't know. Ask us.
Yes. Yes, I think so. I don't think there's going to be anything that different. I mean, we're around A0, as you say. Yeah. So there will be a little effect, but you're accelerating it hard for a long time. And somewhere in the coast phase where you're going to have it, where it's already moving at a huge clip. So I have a hard time imagining that MOND's going to give enough deflection in that time to make a difference.
You're going to crash. But I mean, I was reading actually this morning that the plan is to take bacteria and land them in Proxima Centauri. Right?
Okay, before we get into that,
Kyle. This is about what you brought up about Stacy's law or Renzo's rule, or whatever you want to call
Can you speak louder?
Yeah. So about Renzo's rule. When you say every time you see a feature in the light, you see a feature in the rotation curve, which is, I think, generally true. I guess the thing that worries me about that, sort of agnostic of theory, is that wherever you see a feature is kind of wherever you expect to depart from the assumptions that you're using in the mass modeling, which is, circular orbits, spherical symmetry, these kinds of things. So yeah, I don't think it matters what theory you're in. Just that's where I start to worry about systematic effects in the modeling messing this up.
Well, I think that's fair, and I think I agree with what Carlos said earlier, that makes sense in the high acceleration regime, where it's just the baryons doing the job. But the thing that's concerned me a long time is that I see the same effects in low surface brightness galaxies that are very submaximal for any plausible stellar mass to light ratio. And so there seem to be disk dynamical things going on that want a lot of disk self-gravity and do all the things that you're worrying about, and we're seeing those effects when I don't think we should. That's the trick. The halo ought to suppress all that stuff, I would naively think.
So maybe that's going to end the debate, I don't know, but what if it's both at the same time? What if we have modified gravity
the stream.
and the particle dark matter? How do we get out of that?
Well, and that's why we have ideas like Justin Corey's superfluid dark matter or Luc Blanchet's dipolar dark matter that are kind of hybrids of both, which do everything right, but they feel like a Tycho Brahe universe to me, right?
Nicola, I wouldn't want to live in a universe like that.
So what happens with cosmology? I mean, these are all rotation curves forever, but there is more. Much more, right? CMB peaks, the reproduction CMB. Of course, you need some replacement for GR, but this has to be put in a framework that goes beyond MOND, because there are many, many pieces of information you're not discussing. So the world of cosmology doesn't finish with galactic scales, right? So what about all the rest? For example, we heard actually that at least with Teves or different kind of things that were tried in that way, you can reproduce the first and second peak in the CMB, but not the rest. So shouldn't that be also a concern?
Yes. I mean, I thought I said that, and you know, there's not a lot of time to say these things, but you know, I think what I'm talking about motivates a search for that kind of theory. And I think Dan said yesterday, okay, it's been 35 years and nobody's come up with a satisfactory theory. That's fair. It's been that long and we haven't detected dark matter either, except we've invested a lot more time and effort and money in the latter. Right? It's just a handful. So that's an interesting point. As near as I can tell, there's very little, not all, but very little of cosmology that MOND is inconsistent with. It doesn't give you a theory, right? That's why I started with what lambda CDM does right. MOND doesn't do that for you. But there's nothing about MOND that contradicts any of that.
Well, except that once you introduce dark matter to fix other things, you don't have room for dark matter and MOND to coexist on the galactic scale.
I would like to believe that's true. But does the stuff exist? Right? It's just like the X-Files to me. I would like to believe. Okay? And I did for a long time. But if this paradigm is right, then there are zillions of WIMPs moving through this room right now, and we ought to be able to catch one.
Okay,
so I just wanted to return.
Last quick question from Justin.
So yeah, I just wanted to return to the very interesting point that Carl raised. I mean, I think he's absolutely right, and it can also be true even for low surface brightness galaxies, which I'm pretty sure is what you were also trying to allude to, because, I mean, for some of these galaxies that are quite close to face-on, you can see these very clear giant H1 holes in these low surface brightness systems, and they have velocity features that are correlated with the holes because the holes are expanding. Sure. And so, you know, some of these velocities for these holes can be as high as 30 kilometers per second, which is a fair fraction of the rotational velocity. So that's an example where you see a feature in the gas that's very much correlated with what you would potentially infer for the rotation curve, because it messes up the rotational velocity, which is then not a good representation of the gravitational potential. And you know, you could imagine because stars are forming from the gas, then obviously the gas is correlated with the light, is correlated with the velocity field, and if you demand that the velocity field is telling you the potential, then you'll say, it's correlated with the potential. So I'm not going to claim that this is a complete solution to every bump and wiggle in every galaxy, but I think you can have wiggles in the rotation curve correlate with features in the light, even when the light is subdominant to the potential.
Well, that may well be true, but it doesn't, I mean, that's addressing Renzo's rules specifically, but we do quality control when we put things on the radial acceleration relation. So something that was grossly asymmetric and had obvious non-circular motions, we would say, okay, we don't know what the circular motion is, and we wouldn't use it. Well, let me put it to you this way. Spiral arms, bars, things like that are very natural features that result from disk self-gravity. We see those features in low surface brightness galaxies. You know, that's a lot easier to understand in the context of a theory like MOND than it is in the traditional Ostriker and Peebles sort of picture where the halo would really suppress the growth of those modes. Well, yeah, but then that's a problem for the whole dark matter paradigm, if that's right, yeah? Yeah, but, so this is a hard problem.
Okay, let's head to coffee, and we will be back here at 11 for the remainder of the morning session.